Okay, so I don't have to give a long introduction about quantizing gravity and the issues there, but there certainly are fundamental issues left on the table for the Quantum Gravity Institute to be involved with on formulation of a quantum theory of gravity. One thing one can do in the absence of or in parallel with trying to formulate a quantum theory of gravity, is to look at situations where one has a source of gravity that one might at least assume is governed by ordinary quantum theory, and understand how much and what aspects of gravity have to be quantized in order to avoid inconsistencies. And in particular, it's pretty clear that the Newtonian field of the body better not be definite or whatever, or you get into some trouble with that. But do you really need to have quantized true to gravitational degrees of freedom? Well, you can argue about anything. What I'm going to do in this talk is give you an analysis of a really beautiful gedankenexperiment that had been proposed somewhere in the neighborhood of 5 or 10 years ago by Mare, De Palma, and Giovannetti. And I really think this analysis, the gedankenexperiment itself and the analysis really sheds quite a bit of light on some of these issues, as I will explain now in the rest of the talk. So it's critical that I explain the gedankenexperiment, so I'm going to take a bit of time to do that. I'm going to explain it in words first, and then show you a space-time diagram and go over it again. I think it's easier to do it that way. I think the space-time diagram will make it a lot clearer. So every good quantum information, et cetera, gedankenexperiment or otherwise involves two experimentalists, Alice and Bob. Bob is definitely not me, because both of them have to be skilled experimentalists. And they're each in control of some particle. They're going to be doing very different things with their particle. They're not, et cetera. And by particle, it can be a nanoparticle. It could be, bigger than that. It could be an elementary particle. That's not critical. I'm going to treat this as non-relativistic and as though it's described by Schrodinger quantum mechanics, but I'm not going to use any details of the Schrodinger equation or anything, and that's not really essential. And now there's both an electromagnetic and a gravitational version of this. And I'm going to actually, since it's easier to talk about the electromagnetic version, spend much of my time on that, and then explain the differences in the gravitational case. In the electromagnetic version, we have each of their particles are charged, and I'm going to neglect the gravitational interaction, whereas in the gravitational version, they're uncharged, and the gravitational interaction is all that I'm going to be concerned about. Okay, and now to get going on what's happening in this gedankenexperiment, Alice sends her particle, which I'm assuming initially was in the x direction, but she sends it through a Z Stern-Gerlach apparatus and gets it into a 50-50 quantum superposition of spin up and spin down, with the components separated by some distance d, which is much smaller than the distance she is from Bob. And Bob is going to be trying to measure Alice's, sorry, I'm pressing the wrong buttons, which of the paths Alice's particle is following. So he initially keeps his particle in a trap. Then when the interesting action begins at t equals 0, when Alice recombines her particle. Again, she's a very skilled experimentalist, so she can do any of this with ease. And I don't want to say things about, retaining coherence and all that. I mean, I want to make this into a definite physical thing that she looks at. So she's going to see whether the X spin of the particle returns to the original eigenstate or not. And she does this, her part of the experiment, in some time ta. Also beginning at t equals 0, Bob, well, he might keep the particle in trap, but the interesting case is where he releases it to try to determine which path Alice's particle followed, and he should be able to because of the Coulomb or Newtonian interaction of his particle with Alice's. Again, I'll show you this in the space-time diagram. And now the paradox, the interesting question is, if they complete their experiments within a light travel time, I'm setting c, h bar, later g, et cetera, equal to 1. So I'm using Planck units everywhere. So this is not dimensionally wrong here. If they do things within a light travel time, will Alice's particle be coherent? Meaning, will the spin be in the x direction always? Or not, in which case, if it's totally decohered, it'll be 50-50 plus x and minus x. Of course, with just one experiment, they're not going to necessarily determine this with certainty, but again, the budgets are unlimited and they can repeat this experiment many times. So thereby, the degree of coherence of Alice's particle can be determined. Okay, so here is a space-time diagram with time going upward and the z direction depicted horizontally of what's going on in this Gedanken experiment. I haven't shown Alice's splitting the particle originally in a Stern-Gerlach apparatus way back here in the past, but here is her particle in this superposition of spin up and spin down separated by d, and beginning at t equals 0, she recombines it, and up here she measures the x spin and determines if it's always plus x, meaning there's perfect coherence, or not. In the meantime, Bob is releasing his particle from the trap, and if Alice's particle went on this path, it's a bit closer to Bob. There'll be a stronger Coulomb or Newtonian interaction, so Bob's particle will accelerate a bit more and get displaced a bit more toward Alice. I mean, if we have an attractive interaction, if the particles are opposite charged or whatever, or in the gravitational case, where if Alice's particle followed this other path, then Bob's particle would be displaced a bit less. So if he can determine, if he can measure to some good degree of accuracy where his particle is, he should be able to determine which path Alice has taken. And now sorry, I'm pressing the wrong buttons again. Now we have what would appear to be a paradox, and it's not some trick or some whatever that I'm doing, because we have an argument that because Bob can get some which path information, I haven't calculated how much yet, Alice's particle must be at least partially decohered, so sometimes she's got to measure it in the minus x direction. But on the other hand, Bob is doing things, his entire experiment, in a space-like separated regime from Alice's recombination experiment. So by causality, Bob can't have any influence on the outcome of Alice's experiment, and therefore What Bob is doing is irrelevant, and the fact that he's gotten some which path information can't decohere, can't be associated with any decoherence of Alice's particle. Okay, so the question is Alice's particle decohered? And I've given you an answer that it must be to some degree, but it can't be on account of Bob. And that it isn't obvious what's going on. So in the rest of the talk, I'm going to explain what's going on and what features of quantization, of electromagnetism and gravity are essential to not having a paradox on this. So the first thing to note is that I've left some important ingredient out of the description I was giving back here, which is the electromagnetic field. We really need to take the state of the electromagnetic field into account. So if Alice's particle went to the left, there'll be some electromagnetic field around corresponding to Alice's particle having gone to the left. And it's the electromagnetic field that Bob is really interacting with, not directly interacting with Alice's particle. The trouble is, and that's part of what I'm going to, be able to resolve or get, or evade or whatever in the analysis, is that it's not obvious how to talk about the states of the electromagnetic field, and in particular their orthogonality, which would be associated with decoherence, because this electromagnetic field is partly Coulomb field and partly radiation, or possibly partly radiation. And there isn't any way, in general, at a finite time, separating between Coulomb and radiation. Radiation, we have a nice Hilbert space of states. We know what's orthogonal to what, or how much they fail to be orthogonal. But Coulomb field is not an independent degree of freedom. So these, yeah. These.
In the hydrogen atom, the electric field is classical, so to speak. You put it in the Hamiltonian.
Well, I'm saying it's not, and yeah, Jim was saying in the hydrogen atom, the electric field, there's a microphone actually here. If, yeah.
The system, you give an initial state, you evolve forward. Well, sorry, this is not really worth a microphone. I can set up the initial state and keep the observers out of it because I've postulated an initial state. I have a Hamiltonian. I put in it the Coulomb interaction, just as I do with
that's right, but you're neglecting the radiation degrees of freedom of the electromagnetic field.
But why is that necessary?
Well, if you want to do the Lamb shift, it is.
Oh yeah, but this. It sounds like a simple problem if you're willing to ignore the subtleties of relativity.
Yeah, well, but how orthogonal are these two Coulomb states? This particle is in this quantum superposition. Presumably, the Coulomb field is in some superposition. And how do you calculate how orthogonal they are?
So I can't use the old trick of treating the electrostatic field as part of the potential in the Hamiltonian.
Well, you can, but you won't be able to analyze. You won't be able to analyze the decoherence associated with that.
A very naive question. Can I not write down a Hamiltonian in non-relativistic limit for the three particles? The one particle, sorry, the two particles, a state in which the initial condition is specified, the Hamiltonian is simple-minded, I evolve forward.
Yeah. but it's absolutely essential, as we'll see, and I should
We will see.
probably get on to showing you that the radiation be taken into account. And you'll never, I mean, if you don't take that into account, you're not, this is going to be a real paradox.
Right. I think the confusion for me also is basically something is non-relativistic and Maxwell field is being, of course, treated relativistically.
Yeah.
So this seems like a hodgepodge mixture of things about some sources.
Yeah, but the non-relativistic nature of the particles, I'm just assuming so that I can talk about that and you don't have to start asking me what do you mean by a particle and worry about particle creation of Alice's more of Alice's particles and so on. I'm not, I'm not using, I'm not going to actually write down the Schrodinger equation and have some hodgepodge of quantum field theory with Schrodinger dynamics, although one can do that. I mean, but it isn't, I think the issue here is, I think it's pretty clear. I mean, one does deal with particles in the lab, and one could do this Coulomb or Newtonian field measurement in principle, and I'm asking what happens and how do we think about that?
Okay. So one can just say it is all relativity, special relativity, but we're in a regime in which there is no particle creation.
That's right.
Yeah, that's good.
Yes.
I think that's much conceptually clearer.
Yeah. So, I mean, these Coulomb fields are quite distinguishable. Somebody could really measure the difference over a long enough time. So arguably they'd be, orthogonal states if one had a, and if they were, then Alice's particle is already decohered, and that's the end of the story. But as Bill Unruh has very nicely pointed out, this is very much a false decoherence, because if you adiabatically brought the particles together, the Coulomb states would go back together, and there wouldn't be any decoherence. I mean, if you really got decoherence as a result of this, of course, nobody would ever be able to do a coherence experiment in the lab, well, with charged particles, but similarly with massive particles, and everything is massive. So this formula, which doesn't really mean anything, is not the resolution that I'm seeking. But now we can look on what are the limitations on Bob's ability to get which path information. How well can he do that? And we'll look at also the limitations on Alice maintaining coherence. And there is a fundamental limitation on Bob's ability to get which path information, which comes from the vacuum fluctuations of the electromagnetic field. And basically, if you're looking at the root mean square, I mean, the average electromagnetic field is, well, 0 in the vacuum. I mean, it'll be the Coulomb field average or whatever, average in the case that we're concerned with, but I'm concerned with the fluctuations about that. And over a time scale t, if t is very small, there'll be enormous fluctuations. If you're averaging over a larger time scale, then the fluctuations average out to 0, or nearly 0. So what does that have effect does that have on Bob's particle? Well, as a back of the envelope estimate, you can just see how much Bob's particle gets displaced due to an electric field of this sort of magnitude. And amazingly, the time cancels out of this, and you find that vacuum fluctuations by themselves are going to create a fundamental, noise, fluctuation or whatever in the position of Bob's particle by q over m, the charge radius. So Compton wavelength times the, charge in units were fine structure constant units. And so Bob's particle is basically going to get immediately spread out by this amount, and it's not going to get spread out by more than that amount as time goes on by vacuum fluctuations by this very simple-minded back-of-the-envelope calculation. So the point is that if Bob's displacement is of his particles, if this displacement here is less than Q over M, he's not going to get very much which path information. Well, what is Bob's displacement going to be? Well, we've got basically the difference of the Coulomb fields is basically a dipole field of that magnitude of dipole moment. And again, if we use Newton's second law, that's how much Bob's particle is going, the difference in the displacements. So if you give him a lot of time, he's going to be able to figure out which path. But if you don't give him much time, he's not. Okay, what about Alice by herself? Well, there is a key limit on Alice being able to maintain the coherence of her particle. And that's due to the emission of quantized electromagnetic, since I'm doing the electromagnetic case, electromagnetic radiation. It's easiest to think about this if we just, you'll get the same answer if we do the general case, but if we imagine one of these paths is inertial, but the other one is the one that accelerates to close the superposition, then if one detects radiation emitted, you know that Alice's particle followed this path. So the question is, how much radiation is going to be emitted in that situation? Well, you've got to close this dipole in a time t. The Larmor formula tells you that this is the energy flux that you get from that you're going to get that over a time ta. This will appear in photons roughly of frequency 1 over ta. So this back-of-the-envelope calculation says that you're going to emit these many photons, entangling photons, in closing the superposition. Well, if you're emitting more than about 1 photon, the electromagnetic state will be orthogonal, nearly orthogonal to the vacuum, and that's going to decohere Alice's particle no matter what she does. So you, microphone.
In a conventional two-slit experiment, do I have to worry about this?
In principle, but
in practice?
This dipole is going to be a hell of a lot smaller in these natural units than the time over which you do it.
You know, I've been schooled to say an electron zipping around an atomic nucleus is going to radiate like crazy, but it doesn't, unless it's in an excited level. An electron in the ground state is, you might think, zipping around.
But I mean, this is an electron not in some stationary state, but really you've really got to put it through a Stern-Gerlach apparatus and accelerate it, and it will radiate.
Oh, wait. I pass the wave function through a slit. I eliminate many particles, of course, many events. A wave function coming out spreads. But does that require...
I'm neglecting the wave function spreading. I mean, there are effects that
then what is the... But you understand why I'm nervous. We went to great lengths to get quantum mechanics to stop the electron from radiating when it's in an atom.
But it's going to radiate if you send it on some path and accelerate it. I mean, it's not going to be very different from a...
I worry about acceleration.
You're going to get synchrotron radiation from, quantum electrons as well as classical.
We have to think of this.
Okay.
Keep the mic, Jack.
It's not bound state. But I think about, I go back to Schrödinger, I have a wave moving through a double slit experiment, moving through a single slit. The wave function is in part absorbed and in part passes through and spreads.
Yeah.
And that requires radiation?
No, because it's basically moving inertially.
Yes,
but
yes.
now I have to do something to recombine the paths. So I really have to accelerate.
But in a normal double slit experiment, you have two parts of the wave function spreading
Yeah.
and interfering.
Yeah, no radiation then.
Right.
You don't have to worry about that. But in this recombination, I will have to worry about it.
Wait, the wave. I better stop. Yeah.
All right, just maybe to put an outside voice to clarify this. If you do the double slit experiment, the electron goes through the slit. So you send it in a momentum eigenstate, right? Now it goes through the slit and it spreads out, as you're saying. On each branch of that wave function after the slit, it's been accelerated. So it will Bremsstrahl along and decohere like this. It's just negligible in a real experiment.
Yeah.
Yeah.
Yeah, there will be some decoherence associated with it spreading because there is some acceleration, but that's really more, I mean, that's not, I think what I'm saying here is pretty simple and straightforward. I mean, maybe not correct, but I think it is also correct. I mean, that there will be radiation. Again, I'm neglecting the spreading. I'm bringing these together because I think it's easier to think about the spin coherence and the spin measurement, and I'm neglecting the wave function spreading. But it won't, I'm doing this just because it's easier to think about it and easier to talk about it. Well, easier to talk about it, except maybe with you, but I mean, which is great. I mean, I'm very appreciative of these comments because they are really on point. But I am claiming that you will get decoherence due to this. This is not going to be very big in anyone's actual experiment, but in principle it could be. In a Gedanken experiment it could be, and now we can look at the outcome of the Gedanken experiment. So I'm going to have Alice and Bob perform their experiments within a light travel time, and now it breaks up into two cases. One, which is the case in anybody's lab at present, where dA, the dipole, the q times the displacement, is much smaller than the time, being taken to do the recombination. And in that case, there'll be negligible radiation, and Alice can succeed in her coherence experiment, at least if she were on her own. But what about Bob? How well does Bob do in measuring if he, again, is at space-like separation, does everything in less than a light travel time? Then he's very time limited in how much his different particles are going to respond to the different Coulomb or Newtonian fields. And if you just put things in, you find that the displacement is less than the charge radius. So in this situation, Bob is not going to be able to acquire any significant which path information, and there's no contradiction with Alice maintaining the coherence. On the other hand, in this idealized Gedanken case, where the dipole is large, which in principle could happen, then Alice is going to emit entangling radiation, and her particle is going to be decohered. It doesn't matter what Bob does. It turns out Bob could have measured which path, but Alice already destroyed the coherence of the particle on her own. Okay, so what are the lessons from this case? Well, I claim both vacuum fluctuations and quantized radiation are absolutely essential for understanding what's going on in this Gedanken experiment. If you didn't have vacuum fluctuations, Bob would be able to get which path information in a situation where Alice on her own wouldn't have decohered the particle. And without quantized radiation, Alice would have been able to maintain coherence, but Bob would have gotten which path information, which again is violating some basic principles of quantum mechanics or violating causality. Okay, what about the gravitational case? Well, you might ask, how do I know how to do the gravitational case unless I know how to do quantum gravity? But the whole logic of what's being done here is I'm going to treat linearized gravity as a quantum field, which I know how to do. It's just a spin-2 field, and see what happens. If we run into some contradiction, that indicates something's wrong even with quantization of gravity at this level. And if it works, and you don't get a contradiction, well, that suggests what features a quantum theory of gravity better maintain when we do better than just a linearized gravity field. Yeah, I think I did start late, but yeah, okay. So the differences are now this charge radius becomes the Planck length. So Bob's got to do better than the Planck length. You might think it's the same dipole calculation to see what Bob can measure, but that's actually not true in relativity because you can't make a mass dipole from an isolated system. If Alice's particle goes one way, her lab is going to have to go the other way to cancel that dipole moment. So in fact, the dominant effect is from a quadrupole moment, and that's a much smaller effect than that Bob is going to have to measure. On the other hand, not coincidentally, because it's really for the same reason, the dominant radiation of Alice is going to be quadrupolar, and she's going to emit these many photons in terms of the effective quadrupole and the amount of time. And the analysis then proceeds in exactly the same manner with quadrupole replacing dipole and the changes in the formula. And again, if the quadrupole is small enough, she can maintain coherence, and Bob can't get which path information. And if the quadrupole is large, Bob can get which path information, but Alice is going to destroy the coherence from quantized radiation. Okay, so now what would have been the second half of the talk is that gives an explanation with back of the envelope ideas, but it's not very satisfying because it doesn't really show that Bob can never produce a contradiction. And like if you had n Bobs doing these experiments, maybe you'd reduce the noise or whatever. I mean, vacuum fluctuations are highly correlated, so it's not obvious that you would. So I don't have time now to go through what's in the second of the papers, but the key idea is to look at now the decoherence due to Alice, and we have this problem of separating the fields into Coulomb field and radiation, but that problem goes away if you go to the asymptotic future because the radiation all goes to null infinity, the Coulomb field goes to time-like infinity. There's a completely clean separation. And if you do the recombination at some finite time and just keep a Coulomb, keep the particles inertial and so on, then you can translate this radiation at null infinity to a finite time. The key idea, skip that, this is the same space-time diagram as I was showing you before with Alice and Bob performing their experiments at space-like separations. This is a conformal diagram, so Bob's gotten a little shrunk, but he's quite the same person as he was in the other diagram. And the idea is you can draw two different, because they're doing things at space-like separations, I can consider a time slice that does what I've sketched here. Well, let's do the sigma 2 actually first. On this time slice, Alice, perfectly good Cauchy surface, Alice has not started the recombination, but Bob has completed his measurement. He sees only the Newtonian field of Alice. From this point of view, there's nothing different going on, so that you can consider Bob as measuring the Newtonian field. But if I draw this slice, which goes through Alice after she's completed the recombination and before Bob has started his experiment, then this is pure, well, it's the Coulomb field of the combined particle, the electromagnetic field is, plus something I can describe as radiation. And Bob is now interacting with the radiation and is just measuring properties of the radiation that Alice has already emitted. And these are completely equivalent viewpoints. So this slide, which I would have gone through with a bit of time, shows you that Bob can never, there can never be more decoherence associated with Bob than is present in the radiation states of Alice, because Bob is just measuring the radiation emitted by Alice, even though you could also interpret him as measuring the Coulomb field or Newtonian field of Alice. Those are equivalent points of view. When Bob is making his measurement, he has no idea whether he's an innocent bystander measuring radiation or a destroyer of Alice's coherence by measuring the which path information through the Coulomb field. In a court trial, the key witness, if it's a felony to cause decoherence of someone else, the key witness is not going to be what Bob did, but what Alice did. Because if Alice recombined her particle, then Bob's an innocent bystander, but if she didn't, he's guilty. So the bottom line, and now I'm really finishing, is that, as I've already said, we really need quantized radiation and vacuum fluctuations to avoid contradictions with causality and complementarity. But what I would have showed you in more depth is that within the protocols of this Gedanken experiment, there is absolutely no distinction between saying that entanglement between Alice and Bob was mediated by a Coulomb or Newtonian interaction or was emitted by the emission of quantized gravitational radiation from Alice. But I've exceeded my time, and the chairman has been, the de facto chairman has been very generous, so I'm going to end right there.